Andrej Karpathy just released a project that lets AI agents run machine learning research completely on their own. You go to sleep, the agent runs 100 experiments overnight on a single GPU, and you wake up to a better model. Not hyperparameter tuning, not grid search. The agent actually reads the training code, modifies the model architecture, changes the optimizer, runs the experiment, checks if it improved, and decides whether to keep the change or throw it away. It got 31,000 GitHub stars in 5 days, and the entire thing is just 4 files. In this video, I'm going to walk through exactly how it works, every file, the architecture decisions the agent took, and how you could build something like this yourself. Before we get to the code, you need to understand what makes this project fundamentally different from anything else out there. This is not a Python library. There is no agent framework, there are no LLM API calls, there is no RAG pipeline, no vector database, no orchestration system. The agent is your existing AI coding assistant, Claude Code, Cursor, Windsor, whatever you use. And you program the agent in English. You write a markdown file called program.md that tells the agent what to do. Karpathy put it this way, quote, "The core idea is that you're not touching any of the Python files like you normally would as a researcher. Instead, you're programming the program.md markdown file that provides context to the AI agents and sets up your autonomous research org." End quote. Think about that for a second. The human researcher's job is no longer to write code. It is to write instructions in English for an AI that writes and runs the code. His tagline for the whole project: one GPU, one file, one metric. Let's look at the actual repo. The entire project is 10 files, but only 4 of them matter. Prepare.py is a fixed infrastructure, data loading, tokenizer, and the evaluation metric. Nobody touches this. Train.py is the only file the AI agent modifies. It contains a full GPT model, optimizer, and training loop. Program.md is the instructions for the AI agent. The human writes this, and this is where the magic really is. And py project.2ml lists the dependencies. Let's start with program.md because I think this is the most interesting file in the entire repo. Program.md is about 150 lines of English, and I think it's the most interesting file in the entire repo. Not because of what it says, but because of what it teaches us about how to work with large language models. Let me walk through the key design choices and why they matter. The first thing Karpathy does is isolation. Every research run gets its own Git branch. This isn't just good engineering. It means if you're running multiple agents or if you restart a session, nothing collides. Each run is completely self-contained. Then he tells the agent, read all the files first. Read the readme, read the prepare.py, read the train.py. Get the full context before you touch anything. This matters because LLMs don't automatically know what's in your repo. If you skip this step, the agent will make assumptions, try to modify files it shouldn't, or miss constants defined in a file it never read. When working with LLMs, making sure that the LLMs have everything in context they will need is everything. Next, the rules section. Notice how explicit everything is. The goal is stated in one sentence. Achieve the lowest validation bits per byte loss. Not improve the model, that's vague. Not make it better, that's a different objective. One specific metric, one number, lower is better, zero ambiguity about what success looks like. The time budget is fixed at 5 minutes. This is crucial. The agent doesn't need to decide how long to train. Every experiment is exactly 5 minutes, which makes every result directly comparable. Then, what you can and cannot do. Only edit train.py, cannot touch prepare.py, cannot install new packages. Everything is fair game within train.py. Architecture, optimizer, hyperparameters, model size, but the boundaries are crystal clear. This is a pattern worth internalizing. When you give an LLM too much freedom, it gets lost. When you give it too little, it can't do anything useful. Karpathy found the sweet spot. Massive freedom within one file, but hard walls everywhere else. Now here is my favorite part, the simplicity criterion. Karpathy tells the agent, prioritize elegant solutions. If a marginal improvement adds unnecessary complexity, it's not worthwhile. If you can delete code and get equal results, that counts as a win. This is Karpathy encoding his research taste, his meta-knowledge about what good ML research looks like, directly into the agent's instructions. Without this rule, the agent would just pile on complexity. More layers, more tricks, more special cases. The simplicity criterion prevents that. And then the experiment loop. The steps are straightforward: edit, commit, train, check, keep or discard, and then repeat. But there is one line that makes the entire system work, which is do not pause or ask the human if you should continue. The loop runs until the human interrupts you, period. This is fighting the LLM's default behavior. These models are trained to be helpful and collaborative. They want to check in. They want to say, should I keep going? Or here's what I found so far. But for autonomous overnight research, that instinct kills you. So Karpathy explicitly overrides it. He also handles the failure modes. What if a run crashes? Read the stack trace, try to fix it, or move on. What if it takes more than 10 minutes? Kill it. These seem like small details, but without them, one crashed experiment stops the entire pipeline. The human might be asleep. So that's program.md, 150 lines that encode isolation through Git branches, explicit context loading, one unambiguous metric, freedom within hard boundaries, research traced through simplicity criterion, structured logging, crash recovery, and one critical override, never stop. At 12 experiments per hour, this runs roughly 100 experiments overnight. In practice, you might need to restart the session a couple of times. But the Git branch picks up exactly where you left off. Now, let's take a look at prepare.py. This is the file the agent cannot touch. It's the fixed ground truth. It defines 4 constants: max sequence length, time budget, eval tokens, and vocab size. It handles a data pipeline. The training data is Karpathy's climb mix dataset on Hugging Face, 400 billion tokens of shuffled web text, split into over 6,000 Parquet shards. The tokenizer is a custom 8,000 vocab BPE trained using a Rust-based library called Rust.py with GPT-4 style split patterns. And most importantly, it defines the evaluation metric bits per byte or BPB. BPB is the single number the entire system optimizes. It measures how well the model compresses text. Lower is better, and critically, it's vocab size independent. So if the agent changes something that affects tokenization, the metric still gives a fair comparison. And this is why the file is immutable. If the agent could modify the evaluation, it could cheat. The fixed evaluation is what keeps the experiment honest. Now we get to train.py. This is the only file the agent modifies, and it contains the entire model, optimizer, and training loop. Let me walk through the key technical choices. The baseline model is a standard GPT, a decoder-only transformer, 8 layers deep, 512 dimensions, 4 attention heads, each with 128 dimensions. But there are several non-standard choices that are worth understanding. First, Flash Attention 3, the latest Flash Attention kernels. It auto-detects your GPU and loads the right kernel. This is the fastest available attention implementation. Second, Sliding Window Attention. The model uses a pattern called SSSL, 3 short window layers followed by 1 long window layer. Short means half the context length, long means full context. This saves compute on the inner layers while keeping global attention on the outer layer. Some other settings used are value embeddings from a paper called Resformer. Activation function is ReLU squared. We are using learnable residual scaling, and logit soft capping at 15% is used to prevent any single logit from exploding during training. Now the optimizer. Autoresearch uses a hybrid optimizer called Muon AdamW. For 2-dimensional weight matrices, the big parameter tensors, it uses Muon. For everything else, biases, layer norms, embeddings, it uses the standard AdamW. The training loop is time-based, not step-based. It runs until the wall clock hits 5 minutes. The first 10 steps are excluded for CUDA kernel compilation. The learning rate does a cosine warm down for the last 50%, and if the loss exceeds 100 or becomes NaN, the run aborts. One subtle but clever design choice is how Git is used. Each experiment is a Git commit. If the experiment improves the score, the branch advances. If not, Git reset rolls it back. The result.tsv file is intentionally untracked. It accumulates all experiments regardless of whether they were kept. So at the end of the night, you have 2 artifacts. The Git branch shows the accumulated winning changes, and results.tsv shows everything that was tried, including all the failures. Now here's the part I think is most actionable. You don't need Karpathy's exact setup to use this pattern. The core idea generalizes to anything with a quantifiable metric. The recipe is 3 things. 1, a single file that contains the thing you want to optimize. 2, a fixed evaluation that produces a single number. 3, a program.md that tells the agent the rules. The community has already generalized this. Autoresearch anything applies this pattern to any optimization problem. Autokernel does GPU kernel optimization. There are ports for Mac using MLX and Windows with RTX cards. Here are concrete ideas you could try today. If you're a machine learning engineer, you can use a very similar setup for your own models. If you're optimizing inference speed, make the metric latency or throughput, let the agent try quantization schemes, batching strategies, kernel configurations. The key insight is the constraint. By limiting the agent to one file, one metric, and a fixed time budget, you make the problem tractable. The agent can't go off on tangents. It has to make the number go down. Now the main criticisms. The biggest one, isn't this just hyperparameter tuning? Partly yes, a lot of the improvements are learning rates and batch sizes, but partly no. The agent can also make architectural changes, swap activation functions, restructure the optimizer that goes beyond traditional hyperparameter search. Second, random seed gaming. The agent sometimes gets a tiny improvement by just changing the random seed. This is why it is very important to define the constraints very well in program.md. Third, the agent is timid. Karpathy himself said the models feel, quote, very cagey and scared, end quote. They tend towards small conservative changes. This is a real limitation of current LLMs as research agents. But I think the most important thing about this project isn't what it achieves today, it's the pattern it establishes. Program research in English, constrain it properly, let it run autonomously. The pattern gets much more powerful as the models improve. I want to leave you with one thought. In the README, Karpathy wrote a fictional origin story. He imagined a future where, quote, research is entirely the domain of autonomous swarms of AI agents running across compute cluster megastructures in the skies, end quote. He called this repo, quote, the story of how it all began. It's tongue-in-cheek, obviously, but 5 days after the release, 31,000 stars and 4,000 forks, the community built a distributed version, Autoresearch at home, within days. 3,000 agents across different hardware discovered that optimizations are hardware-specific. Batch halving works everywhere. Swigloo works on Blackwell but not on H100s. These are genuine research findings, discovered not by human researchers, but by a swarm of AI agents running overnight on GPUs around the world. I hope you found it useful. I'll see you in the next one.